this is an iHeart podcast. Guaranteed human.
Work can be a little weird. Cringy training seminars, coworkers who won't stop talking about their plant, forgetting the mute button at an inopportune moment. We have to deal with a lot on any given workday. Sometimes it can feel hard to thrive and move forward in your career. Well, that's where LinkedIn comes in. LinkedIn helps you get ideas and insights from experts in your field, connect with people professionally, grow your network, and access tools designed to help you find the right fit for your next role. Whether you're just getting started, figuring out your next move, or looking to accelerate your career, LinkedIn is built to support you at every stage because LinkedIn is the network that works for you. Visit linkedin.com/knowstuff to learn more.
Hey everybody, when you're at work, you never know when you're going to get interrupted, like when an office fire drill happens right in the middle of your presentation, or maybe construction is going on just outside your window. But with the Dell Pro laptop powered by Intel Core Ultra with vPro, no matter how many interruptions you have, your laptop won't be one of them.
Yeah, with the battery that's optimized for the way you work and built-in intelligence that quiets distractions the moment you're trying to focus, your tech won't slow you down, even when you're getting bounced from an office you forgot to reserve. The Dell Pro, built for those who stay in the flow. Find technology built the way you work at Dell.com/Dell-Pro. Built for you.
Welcome to Stuff You Should Know from HowStuffWorks.com.
Hey, and welcome to the podcast. I'm Josh Clark, and there's Charles W. Chuck Bryan, there's Jerry, and we're about to try some physics. Oh yeah, this is Stuff You Should Know. We're about to try some physics.
Yeah, this did not break my brain like I thought it would.
Yeah, I think it's a pretty surface level explanation, but like it gets the point across, and I don't see any reason for us to try to go any deeper.
No.
I think we would very quickly spin out of control like a up-down quark or something.
Yeah, so dark matter is invisible glue that holds everything together. The end.
The end. We just don't know what it is.
No, we'll get into it, but you might notice, dear listener, a new thing in your feed popping up next week.
Next Wednesday.
Wednesdays, we are debuting a new thing called Short Stuff.
Which is just the cutest name.
It is.
It's Stuff You Should Know, Short Stuff, I guess is the full name.
Probably.
Or not, who cares?
Yeah.
But it's a Stuff You Should Know episode. It's you, me, and Jerry. But over the years of recording, like, we've got these lists of topics we want to do.
So many lists.
And this one, like, part of the list just kept getting bigger and bigger and bigger because there are, like, topics out there that are really interesting, but they're just not big enough for a full episode.
Even with tangent upon tangent.
And we could have been like, well, we'll put like 3 of them together randomly. We thought about doing that once.
Yeah.
It just didn't feel right. So what we did was spin off like a new podcast called Short Stuff, which is just a smaller sized episode of Stuff You Should Know, just because the topic wasn't quite big enough to warrant a full episode or a large size episode. We're doing a small size episode.
Yeah. So look for like 10 to 15 minutes tops. I think we're in the wheelhouse of about 12 minutes.
We seem to like magically hit 12 every time.
Yeah, and it's kind of fun. I think it's a great idea. I'm really happy with them.
Yeah, same here. And I think the first 4 we recorded, we didn't know what we were going to call it yet.
Right.
And I don't believe we went to the trouble of going back and changing that.
We might do that. Are we doing that, Jerry? She just shrugged.
No, she said no. She said that sounds like a lot of work.
Yeah, it would be just like us to just sort of waddle our way into this thing.
Sure. And which is exactly what we did. But hopefully you guys enjoy them. Doesn't cost you anything.
Yeah.
So don't complain. Actually do complain. If they're way off base or they could be better, we want to hear about it.
No, I think people will be like, oh, this is just like a little bite-sized Stuff You Should Know.
That's exactly what it is. It's like a Snickers miniature, but of Stuff You Should Know.
That's right. And you know our love of small things here.
Especially Snickers.
Or like tiny Tabasco bottles. This is the tiny Tabasco bottle version of our show.
Those things are priceless.
All right. So physics, dark matter, go. Let's do this.
All right. So
this wasn't as hard as I thought.
No. And it's actually pretty easy to get across.
Yeah.
Here's the thing. So astronomers have gotten to the point, it's starting in about 1920 on.
Yeah.
Astronomers and physicists and astrophysicists and even particle physicists got to the point where all of their combined knowledge was refined enough that they could look out into the universe and be like, we can figure out how much this weighs.
Right.
To put it more scientifically, we can figure out what the mass of the universe is. It's going to take us a really long time, but we are now at the point where our level of observation and our level of understanding of physics is such that we can do it. We're there now.
Yeah, and it's not just like, oh, well, that weighs this, the end.
Right.
Like knowing something's mass tells you a lot about it, the way it behaves.
And the nature and future of the universe, as we'll see.
Yeah, for sure. So it's not just weight. It's more complicated than that and what weight can tell us.
Right. The problem is you can't just like put a galaxy or star or something on the scale.
They tried.
They have to, it broke the scale pretty quick. It actually vaporized it. But there are ways you can infer the mass of something.
Yeah.
One of the ways that you can infer the mass of a star, from what I understand, is to measure its luminosity, how bright it is.
Yeah.
I've also heard that's a mixed bag because
it seems like it from doing this.
They have different sizes in their lifespan.
Yeah.
I've just heard luminosity and mass is not just straightforward.
Sure.
Like most things in astrophysics are.
Yeah, that's the word on the street.
Right. So when they started getting to the point where they could infer the weight of a star or of a galaxy or of a galaxy cluster, which is basically like a galaxy of galaxies,
yeah,
they started to notice something really weird. All of the matter that they could see, the stars, the gas clouds, the cosmic dust, the everything, matter, things that make up you and me, things that everything has a common basic unit, an atom that is made up of elementary particles like protons and neutrons and electrons, matter.
Every non-living and living thing in the galaxy,
you would think, is made of matter. The problem is they started finding that, this galaxy over here and this galaxy cluster, and everywhere we're looking, the amount of matter that we're seeing is way too small for the amount of mass that the thing we're looking at appears to have. And a cosmological mystery was launched. What the heck is going on was the question of the day.
Yeah, so all that matter that we know about, they call that baryonic matter. And they were like, the calculations are off or something. Like there's got to be something else there to account for this.
Well, that's the two possibilities.
Well, sure. And so way back in, was it 1932, an astronomer, a Dutch astronomer named Jan Hendrik Oort, because he's Dutch.
Sure.
He actually, I believe, was the first person to use the term dark matter. Is that right?
That's what I saw.
So dark matter is a sort of a placeholder name for what they came up with for this, for lack of a better word, this invisible matter that has to be out there. It's sort of like wind. Like you can't see wind, but that doesn't mean it's not out there because you can measure it in different ways, see how it reacts on other things.
Right.
And so they started calling it dark matter.
Right.
This invisible, well, we'll talk about what it ends up sort of looking like in a minute. I don't want to give that away yet.
Right.
But this invisible matter.
That they think is there.
Right, but it doesn't emit or absorb light or electromagnetic energy. So it's way different. It behaves differently such that people were very confused as to what the heck was going on.
And they still are.
Yeah, sure.
So this term dark matter, like you said, it's a placeholder. And it's a placeholder for the current point we are in our understanding of the universe, which is when we look out at galaxy clusters and galaxies and all this stuff, there's not enough matter to account for the amount of mass that we're seeing. So again, that means one of two things. Either there's something there that we can't detect, or our understanding of physics is off. And the term dark matter stands for both of those. It could be a thing, an undiscovered particle or something like that. Or it could be a misunderstanding of physics that we need to eventually correct. Either way, there's a lot of mass that is unaccounted for throughout the universe. And it seems like there's a lot more what we call dark matter than there's regular matter. And the more we look into it, the more it seems like there's something there that we haven't discovered yet.
Yeah, so right now, baryonic matter, all the stuff that we know about, counts for about 4.5%. 23% of where they peg dark matter. Then we have something that I don't even know if I ever want to cover called dark energy, which makes up the other 72%. Mm-hmm. But they know it's there because there's something out there that we can't account for that has a significant gravitational force.
Right. That's where the whole thing started, where they first detected it.
Right.
So when they first started looking out at galaxies and stuff like that, there's this whole thing that Newton came up with, the second law of motion.
Yeah.
And this is like a tried and true law. It's a law. This isn't Newton's suggestion of motion,
right,
or Newton's second, what about this of motion? It's a scientific law. That's how, that's as proven and accepted as a scientific observation can be, is to be made a law. And it said that when you're looking at a galaxy far, far away, and the most of the matter is accumulated toward the center of the galaxy, then that means most of the mass is accumulated toward the center. Okay?
Yes.
Okay. So that means that the stars near the center are going to spin, they're going to rotate around the galaxy a lot faster than the ones on the fringes, because the ones on the fringes are going to go a lot more slowly because they're further away from that center of mass. So the gravitational pull is going to be weaker.
Yeah, I mean, that's the easiest way to say it, is in the center, you have more mass. More mass means things are spinning faster. There's more gravitational pull.
Right.
So all the astronomers supposed, like you said, the stuff on the outskirts are probably hanging out there spinning a lot slower.
Right. Well, when they looked, they found that's not the case at all. As a matter of fact, the stars on the outside are spinning around the center of the galaxy just as fast as the stars near the center of the galaxy, which makes zero sense.
Yeah, it's almost as if there's some invisible force out there.
Right. Like if you look at this this galaxy, the situation that they started to find, and it wasn't just one galaxy, they found it in this galaxy too, in this galaxy too. And even stranger than that, they found it in those clusters, those galactic clusters. So rather than stars that make up a galaxy, this is galaxies making up a huge giant mega galaxy. The same thing happened. The galaxies on the outer edge of the cluster were circling just as fast as the ones toward the center. And it just must have knocked their socks off. I can't imagine how many times they went over the same formula to make sure that they had gotten it
this
right.
Is, for clarity, this was the 1950s and 1960s is when they discovered.
They first noticed this.
Yeah.
Okay. So what they figured out was that either there was something really wrong or there was something that they hadn't picked up yet, because those stars on the outer edges of the galaxy, or those galaxies on the outer edges of the cluster, for as fast as they were flying, they should have spun off into space.
Yeah.
There was something missing that explained what was holding that galaxy or that cluster together as fast as the stars of the galaxies were spinning around on the outside. That was the first clue that something was way up with that astronomy was missing something big.
Right. And they knew this was off because they had been using luminosity, like you said, to take measurements for years.
Right.
And it was pretty good. But then when they started measuring the rotational velocity of things, like how fast something was spinning in relation to where it was, like toward the center, it like you said, there was a missing ingredient there that didn't match whatever these luminosity readings were showing.
So you're right. Luminosity was clue one. The angular rotation was, or acceleration of the outer stars was clue number two. So now we've got two different ways of measuring the mass and gravity of remote bodies in the universe.
And they don't align.
Our point, well, they're aligning in that there's something missing here.
Right.
And I think that's a pretty good cliffhanger for a break, don't you?
I think people are going to be like, what?
Yeah, well, why don't you guys go listen to the first half of this podcast or first part again, and we'll see you after these messages. Hey, everybody, we're here to talk to you about Wayfair. who believes that spaces should be functional, they should be comfortable, they should be well-designed, and they can be well-designed by you with their help.
Your updated space should feel more comfortable, inviting, and practical for everyday use. And we're talking about outdoor seating. We're talking about grills. We're talking about major appliances. If you need storage solutions, Wayfair can help you out. Patio lighting, rugs, decor. It is your one-stop shop for home.
Yeah. I mean, it's getting nice out, so it's time to think about living outdoors for the next few months. And Wayfair knows that outdoor furniture, it's heavy, it's intimidating to assemble. So Wayfair has stepped in and said, we're going to handle the hard part so you don't have to.
That's right. You can shop Wayfair Verified, your shortcut to the good stuff. And that means their team of product specialists are going to vet everything by hand using a 10-point inspection, testing things like, quality materials, functionality, and features, and even how long it takes to build that piece of furniture. And the overall experience save time, reduce hassle, and improved convenience.
Patio season is here, and these deals won't last. So head to wayfair.com right now to get your outdoor space ready for way less. That's WAYFAIR.com.
Wayfair, every style, every home.
Hey, everybody. I want to talk to you a little bit about Tide Evo because it represents over 10 years of innovation and product development. Tide Evo is a first-of-its-kind technology where tens of thousands of minuscule fibers are spun together to form a 6 times powerful layer packed with scrubbers, brighteners, pre-treaters, and fresheners. And that's going to deliver a breakthrough clean that's so powerful, it feels like magic.
Yeah, it is kind of like magic. Tide Evo is revolutionary. A 100% concentrated, waterless laundry tile that's made of compressed microfiber soap layers rather than liquid or powder. And it's not like pods or sheets because it uses 6 layers of detergent fibers to deliver superior cold water cleaning without plastic packaging of any kind. And it provides a mess-free, lightweight solution that dissolves lickety-split. So whenever you run into a laundry challenge, turn to Tide Evo. It's revolutionary. It's magic. Try new Tide Evo. Real laundry magic. I really hope we're putting this well. I feel like we are, but sometimes, you just can't tell.
No, this isn't the Sun Redux.
I hope not.
No. This is much more simple.
Okay.
So, like you said, they not only studied regular galaxies, but they started to study what you referred to as, and you didn't make it up, but galactic clusters, these knots of galaxies, could be thousands of them, could be hundreds of them. Mm-hmm. But they are bound together by gravity, and they were like, you know what, let's study these because maybe what we can find, or, this is what we suppose at least, is there might be these big giant pools of hot gas that we never could detect before, and that would account for all of this mass.
Right.
And they did find these superheated gas clouds, and we're like, great, that's it. But they're like, no, that still doesn't account for everything.
That's like a small percentage of what needs to be accounted for.
Right. So it was a breakthrough, but it wasn't the solution solver that they were looking for.
It was because if you can find something that we know has mass, like huge clouds of gas. That, again, a particle has mass, and if you put enough particles together, it has a lot of mass. If you could fill in the blanks of the missing matter that explains the mass of this thing you're looking at, great, especially if it's something we already know about, like hot gas. And they did find some hot gas, but say that explained 5% of the missing mass. It didn't explain everything. And what that did do also was, okay, we've gotten that much more sophisticated, and it still hasn't answered this dark matter thing. It's pointing to the idea that there's something we haven't discovered yet that is accounting for all of this.
It's very foreboding.
It is, but it's also, I think, very exciting.
Sure.
Yeah.
Yeah, for them and us.
Sure.
So the other thing that happened when they started studying these galactic clusters was that they found out that these clusters and superclusters can, and this is really neat, you can look up images of this, it can distort space-time because their mass is so great. Mm-hmm. So if you're on planet Earth and there is a light, so you're looking from like a telescope on Earth, you're looking at a distant light, like who knows how far away.
Like a star 3 billion light years away.
Sounds great. in between you and that is a galactic cluster, let's say, that will act as a lens. And depending on where it's situated to where you are relative on Earth, it will distort that light into one of several things. If you're in perfect alignment in it, it's going to form what's known as an Einstein ring. And if you look it up on the internet, it's like this beautiful like circle of light.
Yeah.
It's really cool looking.
Yep.
It could be elliptical or oblong. They call it the Einstein cross. Basically splits it into four.
That's
it'll just look like four little stars all like perfectly aligned.
4 copies of the same image.
Yeah.
Yeah, and like a cross.
Yeah, perfect cross. Or it could be a cluster. And this one is sort of cool just because it's like kind of scattered. It looks like a bunch of like arcs and banana-shaped arcs and arclets.
But it's all different versions of the same image that you're seeing. And what you're seeing is that faraway star, but you're seeing it through that galaxy cluster.
That is a distortion of space-time.
Right. That the mass of these clusters are so big and so huge that the gravity in them bends light.
Yeah.
Just like a mound of glass can bend light.
Yeah, like
optically.
a magnifying glass.
Same thing. Now, we have gotten to the point where we are so good at math and physics that we can look at that reflection, that bend, and say, this galaxy has that much gravity. And since this galaxy has this much gravity, it must have this much mass.
Yeah.
Now, if you take that number, this much mass, and you examine the luminosity of the galaxy,
there's that difference.
Yeah, you're like, this is like not off by, like the luminosity is 10, but the mass is 10 and a half.
Right.
There's like sometimes factors of like times 100.
Right.
Sometimes like there's just no way that your math is off. There's a huge discrepancy. So there's a third clue that there's something missing.
Yeah, I mean, that's basically all these are little hints along the way that we're still not able to account for something with our calculation.
Yeah, and rather than the better and more sophisticated our observations and exploration of space and the universe becomes,
right?
It doesn't become like this blank is not getting filled in. It's just becoming clearer and clearer that blank is really there.
Yeah, exactly.
There's a void in either our understanding or our discovery.
So then computers started getting better and better and more advanced.
I love how this article puts it. They turned to the computer. It sounds like they turned to the bottle or something.
Yeah, to compute. So computers started getting so good, and our knowledge of what was out there and our measurements of matter and mass was so great that we could take a pretty good guess on how much baryonic matter there was out there, maybe how much dark matter there might be, design a program and a model that you could feed this information into to spit out what it might, quote, look like, end quote.
Yeah, they basically said, this is how much baryonic matter we think there is. This is how much dark matter we think there is.
Like, map it out.
Go, computer. And
they hit start on the Whopper machine, and it spit out what was sort of like it turns out that it wasn't on the edges. It was everywhere. It was like a web that wound through everything, invisible to us, that sort of acted like this cosmic glue.
Yeah, and so in some places it clumped. In other places there were long filaments, and it kind of looked like it had galaxies or galactic clusters trapped in a spider's web.
So cool.
But it just permeated everywhere. And like you said, it seemed to be like this cosmic glue or cosmic connective tissue. And it was pretty surprising. So they said, okay, well, that's the computer's take. Let's see if we can replicate that. And that kicked off a series of projects that are still going on today to map dark matter in the universe, which I want everybody to stop for a second, because this is about as nuts as it gets. They have gotten to the level of sophistication where astrophysicists are mapping in 3D models stuff that isn't there.
Well,
they're mapping 3D models of voids.
Yes.
Based on how much light bends around a galaxy 3 billion light years away.
Yeah. Not miles, light years.
Right. And then using that to infer the gravity and then the mass. And then they're using that information to create a 3D map of something that may not exist.
Yeah, and the coolest thing about all this to me is it's based on stuff that Isaac Newton and Einstein came up with.
Right, yeah.
And, well, we won't spoil it, but they weren't wrong.
But that is nuts. This is either physics has gone totally insane, or this is the pinnacle of human ingenuity thus far.
Well, thus far, for sure. I'm glad you added that. So let's talk about a couple of these. About 7 years ago in 2011, there were a couple of teams using data from Chandra's X-ray Observatory. Mm-hmm. And what they're trying to do here, like you said, is create this real map based on direct observation instead of this speculative computer map.
Right.
What they found out is the computer map was pretty on, which was great.
Yeah.
But they needed the real thing. So they are looking at a cluster, or have been, called Abell 383, 2.3 billion light years from Earth. Mm-hmm. And what they saw was what looks like sort of a football, an American football, or an Aussie football for that matter.
Oh, are they similar?
I just got one in the mail. I bought one.
You need to get Simon to sign it.
Go Melbourne. I should. But it would cost so much to ship it there and back. Maybe I'll just see Simon again one day.
Is Melbourne your team now?
Yeah, that's who I got on.
That's good city.
Yeah, I like it. So it looks like a football with one end pointing toward us, or we're on Earth, so we're the observer in this case. And here's the one thing they didn't agree on, though, was the density of the dark matter on Abell 383
in the center.
Yeah, which is weird because some people calculated it was more dense in the center and matter increased, and other people said it was the opposite. Not like, well, we're not sure, but they thought it was less dark matter at the center, which is a big deal.
But they both came up with virtually the same shape and same orientation, separately and independently, which showed we're onto something, or else, again, we're all collectively out of our minds.
Right.
Based on some shared delusion that we're all working under.
Right. Then there was another one. This one is super cool. In January 2012, anytime I see international team of researchers, I get excited. Yeah. But the Canada-France-Hawaii telescope has a 340 megapixel camera. Mm-hmm. So you can actually take pictures of stuff that far away.
It's like the iPhone XS camera.
Is that one of the new ones?
Yeah.
Okay. Is it good?
I think it's a pretty good camera.
All right.
It's not 340 megapixel.
No, it's not.
But I have to say, I've been to this observatory before.
Oh, really?
It's really cool.
Did you look at did they have photos on display and stuff?
No. They had like telescopes that you walked around and looked out into the universe on. It's amazing.
Did they let you take pictures?
Yeah, I guess so, with your phone.
Oh, I thought you meant, with the 340 megapixel camera. No?
I'm sure they were taking pictures. They didn't give them to us or anything. But what's crazy is it's on Hawaii, so it's just hot and muggy and humid. And then you drive up this mountain and you're like freezing in a North Face coat with like a hat on.
Yeah.
And then you just go back down the mountain and it's Hawaii again. It's a very, great. Very cool experience.
So what they did here was basically stitched all these photos together. It was like photos of 10 million galaxies in 4 different regions over 5 years. Mm-hmm. Stitched it all together, and what they finished up with was basically saying that computer model was pretty on target.
Yeah.
Because what this looks like is what it spit out so many years ago.
Yeah. So they're definitely onto something, it seems like.
Should we take another break?
Yes.
All right. We'll talk about what dark matter is. Hint, we don't know. Hey everybody, I want to talk to you a little bit about Tide Evo because it represents over 10 years of innovation and product development. Tide Evo is a first-of-its-kind technology where tens of thousands of minuscule fibers are spun together to form a 6 times powerful layer packed with scrubbers, brighteners, pre-treaters, and fresheners. And that's going to deliver a breakthrough clean that's so powerful, it feels like magic.
Yeah, it is kind of like magic. Tide Evo is revolutionary. A 100% concentrated, waterless laundry tile that's made of compressed microfiber soap layers rather than liquid or powder. And it's not like pods or sheets because it uses 6 layers of detergent fibers to deliver superior cold water cleaning without plastic packaging of any kind. And it provides a mess-free, lightweight solution that dissolves lickety-split. So whenever you run into a laundry challenge, turn to Tide Evo. It's revolutionary, it's magic. Try new Tide Evo. Real laundry magic.
Introducing the all-new Mazda CX-5, featuring more connection.
Hey Google, where's the nearest Pilates class?
Safety that has your back. More discovery on the scenic routes. More passion in the details. And more control in changing weather. The all-new Mazda CX-5. More to move every side of you. See it in 5 films at MazdaUSA.com/5sides.
Google is a trademark of Google LLC. Sequences shortened and simulated.
All right, Chuck, we're back.
This is where I start to get a little, brain breaky. I understood all that stuff, but this stuff is where I was like, what?
Well, we're transferring from astrophysics to particle physics.
Maybe that's my hang up.
And particle physics is hard. I actually had to teach myself particle physics to write one episode of The End of the World.
Maybe that's my problem.
It's and even still, I'm like, wait, what? It's really hard to understand.
Yeah, I've always been an astrophysicist, though, at heart, I think. So that's just goes against my nature.
Okay, I'm with you. But they're very much tied together. Like, you need particle physics to explain these larger cosmic structures.
Right. So the big question here is, at the end of the day, is it the fact that we just can't really observe this stuff and it's just like all the other matter? Or is it some new matter that we don't even know about yet?
That's the question.
That's the big question.
Or the third option is that our understanding of physics is wrong.
Right, which means, well, we'll see. Some people go back and tamper with things Newton said.
Mm-hmm. He doesn't like that.
Much to the dismay of
Newton, kill brain. So if it's just stuff that we already know exists, but we just can't observe yet,
yeah,
those fall under the umbrella of MACHOs. Massive compact halo objects.
Right.
Which are huge, massive structures that we already know about. Neutron stars, black holes, brown dwarf stars that are huge and massive and have a tremendous amount of mass and thus exert a lot of gravity around them, but are too dim to show up clearly when we're looking at, say, a galaxy or galactic cluster.
Yeah, like we talked about luminosity. They have low luminosity.
Right.
We know they're there, but they're not shining.
But we don't know that that's them. That is one proposal for what dark matter is. They're just things that we already have identified know exist. We just can't see them in these particular things.
Right.
That's actually doesn't have, for as Occam's razory as that is, that actually does not have as much support in the physics community as the other idea that dark matter is made up of some particle that we have not discovered yet.
Yeah, so that's where I got a little confused with the WIMPs and the SIMPs.
Okay.
WIMP stands for weakly interacting massive particles. Mm-hmm. Huge amounts of mass, but difficult to detect because they just interact weakly with ordinary matter. Right.
Here's why they're difficult to detect. They interact weakly with matter. That's not stating it very well. There's the weak nuclear force. Is one of the 4 fundamental forces, and it's found almost exclusively in the nucleus of an atom. Uh-huh. What these WIMP particles, weak interactive massive particles, they're hypothetical. We don't know that they exist.
Right.
But mathematically, they fit the bill of dark matter. The fact that they interact with gravity and with the weak force only means that, no, we can't detect them. We don't have weak force detectors. We have detectors along the electromagnetic spectrum.
Right.
So everything we do when we look out in the universe, we use X-rays or microwaves or radio waves. All of those are electromagnetic.
Right.
If these particles don't interact with the electromagnetic force that has no effect on them whatsoever,
Right.
we have no way of detecting them.
Right.
All we can do
makes sense.
is since they have a gravitational pull because they have so much mass,
Yeah.
we can just sense their gravity and be like, what the heck is going on?
Right.
Which is exactly the position we're in now.
Okay.
WIMPs were a big, they were promoted as the particle, I think starting in the 80s.
It seems like an 80s thing.
Because it does, doesn't it?
A little bit.
Because there was something called the WIMP miracle, and this breaks my brain.
Yeah.
But apparently, if you take the relic density, which is really unimportant for getting into here, but say the density of a WIMP, like how dense the universe would have to be for a WIMP to exist, it corresponds with the weak force number, and that made everybody say, oh, well, they're particles that don't interact with the electromagnetic force. They just interact with the weak force. Nowadays, they've kind of moved to the strong nuclear force.
SIMPs.
And the strong nuclear force also is found just basically in the nucleus of an atom. It's the thing that holds an atom together super tightly.
Yeah.
Holds the quarks into the proton and holds the proton what's the neutral charge one?
Neutron?
Yeah. The neutron and the proton together and keeps them together. That's the strong nuclear force. And they think that is probably the particle now. So
Interesting.
Same thing, though, doesn't interact with the electromagnetic spectrum, so we have no way of detecting it.
Right.
But it would still have mass and hence exert a lot of gravity.
So that's sort of the takeaway.
Right.
Gotcha.
Yeah.
Well, not everyone is on board with this, period. Like some people, there are some astronomers out there who say, they dare say, maybe Newton got it wrong.
Yeah.
And maybe we should crack open the Bible and rewrite it like Thomas Jefferson.
Mm-hmm.
And
that was a good episode.
In the 80s, there was a dude, a physicist named Mordecai Milgrom.
Great name.
He suggested that Newton's second law of motion, which is force equals mass times acceleration.
Which I got wrong in the board breaking episode.
That's right. But we're not physicists.
No.
We just play them on the air. He said, maybe we should look at that again. And maybe he was wrong, and maybe we should modify this. And he called this modification MOND, the Modified Newtonian Dynamics. And the way that I read this was, it almost sounded like, it's probably not quite right, but it almost sounded like he had some answer, so he was sort of rewriting the question to fit.
Yeah, it was ad hoc.
Yeah.
Is what he was called out on. That it wasn't like, oh, here is a new understanding of a physical law around the universe.
Right.
This just applied to those galaxies and their rotational momentum or rotational acceleration.
Yeah.
His whole position was that breaks down at very small accelerations.
Right.
Like a planet on the outside or a star on the outside of a galaxy.
But over a long distance.
Right.
Yeah.
And so a lot of people were like, that's ad hoc. It doesn't hold any water.
Anyone can do that.
Get out of here. Yeah. And then apparently there was a study in 2007 that showed that even down to accelerations as slow as 500 trillionths of a meter per second squared, which is really low acceleration, Newton's second law of motion still held fast.
That is so awesome.
So MOND is pretty much out the window from what I understand.
And Newton is giving the finger from the grave. Like, see what you get?
He very famously liked to say, bite it.
That's on his tombstone, I think. What else do we have here? Alternative-wise.
This guy, I love this dude's name. I looked it up. Dragan Hajdukovic.
Oh, is he one of the guys at CERN?
Yeah, I can do better than that. Dragan Hajdukovic. Sorry, Dragan. But yeah, he said that there's such things as gravitational polar opposites.
Right.
That particles and antiparticles have not only opposite electrical charges, but opposite gravitational charges.
Yeah, so if those are near a galaxy, then it would strengthen, sort of like a magnet almost.
Yeah, they'd form a dipole.
Yeah, so it would strengthen the gravitational field, so that's what's accounting for...
Right.
In fact, I guess he's saying there is no dark matter, right?
Yeah, he's saying that that's dark matter's dipoles, gravitational dipoles, which is interesting because that means if that's correct, then if you got your hands on an antiparticle, it would fall upward. because it would have an opposite gravitational energy.
Yeah.
That's pretty neat.
That is pretty neat.
I would love to have like a pencil made of antiparticles. You just be like, watch this.
Right.
Just knock everyone's socks right off.
So should we talk about
That's what I would do if I had a whole bunch of antiparticles. That's where my imagination ends.
Should we talk about the Big Bang a little bit?
Yeah, because this is the thing. Like, if you've been sitting here going like, come on, why does this matter at all? It actually does matter if we want to figure out how the universe can possibly end.
Right, which is your specialty these days.
Man, I'm so excited about this coming out.
Yeah, we're talking again, Josh's upcoming 10-part series.
The End of the World.
The End of
Josh
the World
Clark.
with Josh Clark.
Yeah, it's slated to come out November 7th.
Yeah.
Man.
And it's this and more, times 10.
Mm-hmm.
Literally times 10.
Yeah.
What other stuff you talk about? AI, I know that's in there.
AI, reckless experiments with viruses.
Oh, geez.
The Fermi paradox, the Great Filter, the whole thing's about existential risks.
Man,
It's
you're getting smarter. I'm just talking about the old movies.
It's a downer. Yeah, but you're like getting in there with people, you know? Like you're getting into the heart of people. It's just different. It's not better.
Well, you got interviews and stuff, though, with like leading experts, right?
Yeah, but I kind of use them as like a Greek chorus to kind of chime in and help like explain it or be like, yeah, Josh is actually right here, you know, that kind of thing.
Sure.
Like it's not just me saying this, you know?
All right, so look for that, everyone. But with the Big Bang, the idea is that the universe is expanding. And the big question is, what's the end game there? Are we going to expand forever?
Right.
And what does that mean in relation to dark matter?
So again, this is the point that we're at. We've actually figured out what the density of the universe has to be. There's something called a critical density, and it's 10 to the negative 29th grams per cubic centimeter, which this article says is equivalent to a few hydrogen atoms in a phone booth. That density of matter.
Yeah.
And if that is the critical density of matter in the universe. If it's more than that, equal to that, or less than that, there are 3 different possible outcomes for the universe, depending on how dense the universe is with matter.
Right. And a phone booth, everyone, is a box that used to hold public telephones that you would step into to make a call.
Yeah. What's a good movie you can go watch to see?
There's one called Phone Booth.
Oh, yeah. I said a good movie, though.
Oh, right. Superman changes his clothes in a phone booth.
There you go. Go watch the original Christopher Reeve Superman.
Right. Or imagine if you were laying dead in a casket and someone sat you up and you were on your cell phone.
But you were only 3 hydrogen atoms.
And your cell phone was connected to a machine by a cord.
Right, exactly.
All right, so where were we?
We were talking about the critical density of the universe.
Right, so there are a few different outcomes here that they've come up with.
Right.
As far as where we're headed?
Yeah. So if the universe has a density of matter, all the matter in the universe, if you could just slice the universe up into phone booths,
yes,
and equally spread out all of the matter in the universe across all those phone booths,
right.
If that equals just a few hydrogen atoms per phone booth, again, that's the critical mass density. And if that is actually the same as the density of matter in the universe, then what we have is a universe that keeps expanding forever, because the universe started inflating at some point after the Big Bang.
Yes.
And this was a huge discovery in and of itself.
Sure.
Right? Everybody thought the universe was just kind of there and unchanging.
Yeah.
No, the universe is actually expanding in size. It's inflating, and the matter in the universe is actually spreading away from it. So everybody's like you said, what's the end game about that? If the universal mass is the same as the critical mass density, it's going to just keep expanding forever. But eventually it'll get kind of cool and everything's going to die and stop. I think it's called the heat death of the universe.
Yeah, and that's called the critical or flat universe. If the actual mass density is greater than the critical mass density, they call that the big crunch. That's not good. A closed universe, that means it'll expand and then eventually slow down, stop expanding, and then collapse on itself.
Right. Like, you know those bungee swings?
Yeah, my daughter was just on one of those.
Okay, so
where they launch her up in the air?
Right.
Yep.
Well, she went that way, and then she came back this way.
She did.
So when you come back this way, when she came back this way, is because the universe is closed, and the gravity because of the mass was greater than the critical mass density. And so gravity overcame it and brought it back together in what was called the Big Crunch, which I'm assuming she did not undergo.
I tried to explain that to her, and all she said was, again.
I don't blame her.
And then finally, we have another outcome. If actual mass density is less than critical mass density, then we keep expanding, but there's no change in the rate of expansion. We don't start expanding faster and faster.
Right. And I think nothing really cools off. It just keeps going forever, which is kind of the all good one, really.
That's called the Wooderson universe.
Right.
Yeah.
All right.
Or specifically the coasting or open universe.
I like that.
AKA Wooderson.
So the only way to figure this out for sure is to live until the end of the universe, and we're talking billions, possibly trillions of years into the future.
Right.
Or we could just figure out how much matter there really is. The problem is, even if we can account for all the regular matter, every bit of things that makes up you, me, and everything we can see in the universe, we still have to account for dark matter. Hence the reason why people are mapping dark matter, so we can figure out truly how much matters in the universe, and then we can predict how it's going to end.
Yeah, it's not just folly and like, hey, this would be neat.
Right. I mean, part of it is.
Yeah.
There's a peanut butter sandwich and a glass of milk at the end of that calculation.
Yeah, that's true.
And I want to say you got anything else, but I'm not going to say that.
I got nothing else.
All right. Well, that's dark matter. Don't even get us started on dark energy. Please, God, don't get us started on dark energy. If you want to know more about dark matter, type that word into the search bar or those words in the search bar. And since I said that, it's time for listener mail.
I'm going to call this something on game shows. Okay. Hey, guys, always wonder what it was like to have a moment where they say, I have to write into stuff you should know for listener mail. Well, I just had that moment. Yesterday, I listened to the Select podcast on game shows. Mm-hmm. That wasn't a Select podcast. It was just a live show.
Oh, yeah.
Right?
Yeah, they fooled me.
I love all your episodes, but I found this one particularly fascinating. Flash forward to this evening, my fiance and I were sitting down to watch a movie. I'm not much of a movie person. Sorry, Chuck. So I told Peter, guess her fiance, to just pick something to watch. He puts on Quiz Show.
Oh, I saw this email.
Not realizing it was based on the real-life event. So I started telling Peter about your podcast and how quiz shows like this one on the movie were rigged in the 50s and it almost killed game shows. I was like a sponge releasing all the information I had heard yesterday. The chance that he selects that movie the day after I listened to your podcast just blows my mind.
It's pretty awesome.
It's a Mandela effect, right?
Syncretism.
Anyway, thank you for what you do, for keeping me company as I drive around D.C. on the Beltway every day.
Oh, you poor person.
I know. When one of your episodes queues up, I know my drive will go so much faster. Lots of love, Kristen.
Thanks a lot, Kristen. That was a great email. We're glad we could help you out, make you look pretty good in front of Peter.
Yeah, good luck with the upcoming wedding.
Yeah, which we assume is impending.
Sure.
Okay. Well, if you want to let us know you're getting married, let us know. We'll say best wishes. Every once in a while, somebody will send an invitation in.
It's always nice.
We've not taken them up, but we usually sign it and send it back at least.
Yeah, I mean, if someone was getting married here in the studio on a Tuesday at 1 o'clock, we'd be there.
And we'd also be like, we need the studio.
Yeah, exactly.
So maybe make it 12 o'clock.
Agreed.
If you want to get in touch with us, you can hang out with us on social media. Just go to, what's our website?
StuffYouShouldKnow.com.
That's right. And you'll find all the links there. And you can also send us an email. Just wrap it up, spank it on the bottom, and send it off to stuffpodcast@howstuffworks.com.
For more on this and thousands of other topics, visit howstuffworks.com.
The next time you end up with something on your shirt, don't turn to your usual detergent. Check out Tide Evo. Tide Evo represents over 10 years of innovation in product development. It's a revolutionary 100% concentrated waterless laundry tile made of compressed microfiber soap layers rather than liquid or powder. It's not pods and it's not sheets. It uses 6 layers of detergent fibers to deliver superior cold water cleaning without plastic packaging. It's mess-free, lightweight, and dissolves quickly. Try new Tide Evo. Real laundry magic.
Geico presents a 30-second podcast between your podcast. Today's story is shared by one of our listeners. It's called Betrayed by Bill. It was in that moment I caught who was staring back at me in betrayal, or more like what? my insurance bill. With trembling hands, I grabbed my phone and switched to Geico, saving about $900 in the process, and never to be betrayed again. Now that was bloody riveting.
It feels good when the story ends with savings. It feels good to Geico.
This is an iHeart podcast. Guaranteed human.